Okay, after getting a little bit of feedback, decided to try a little bit of a walkthrough here for the activity, so you can use this to help as well. So we'll get right into it. You can obviously read through the steps for solving linear equations. This is the most basic type of equation that you're going to find, so this should hopefully go pretty quickly for you. Again, looking at our first equation, 5x minus 36 equals 9, we're going to add 36 to both sides, and we end up with 5x equals 45. Then we're going to divide both sides by 5, and we end up with x equals 9. Next one, we have x's on both sides of our equal sign. So first thing we probably want to do is try to remedy that. So I'm going to subtract the 2x from this side, and I end up with now 7x plus 45 equals 17. Now it's just like the problem that we had previously on part A. We're going to subtract 45 from both sides, and then we're going to divide by 7, and then we get our final answer of x equals -4. Part C, a little bit of a twist on this one. We've got fractions. Don't like using fractions that much if I don't have to. So because I see an equal sign, one of the things that allows me to do is I can multiply both sides by things, or divide or add, just like we did in these previous solving examples. So what I'm going to do here is I'm going to find something I can multiply by that would get rid of these fractions, and that number would be a 3. So what I'm going to do is I'm going to multiply both sides of the equation by 3. Make sure that we distribute 3 times everything in the parentheses on both sides of the equations. And when we do that, we get a 9. And then what happens here is the 3's are going to simplify out. So we just have minus 4x multiplied by 3, and we end up with no fractions. So now this problem looks just like the one that we've had over here on part B. We're going to try to get our x's together. So I'm going to add 4x to both sides. I end up with 9 equals 20x minus 27. And then I'm going to add 27 to both sides, and I get a 36 equals 20x. Divide by 20, I get 36 over 20, and I think that simplifies because I can divide both of those by 4, and I get an x equals 9/5. So there's number 1. All right, so let's get into number 2, solving linear inequalities. We've got the directions there. We solve that just like it were a linear equation. We just have to be aware that when we multiply or divide by a negative number, we'll need to switch the direction of the inequality. So that'll come up a couple of times as I go through my solving steps here. Again, treat it just like it were an equal sign. So I'm going to try to write this this time as I draw it. So as I'm solving part A, I've got -4 I need to add on to both sides. So I get 5x is greater than 55, and divide by 5, so I get x is greater than 11. It says here we're supposed to use interval notation. They have an example of that up above as well. So I need everything from 11 up to positive infinity. X has to be greater than 11. So I'm going to use 11 and then up to infinity. And since it's not equal to, and I just want to start everything a little bit above 11, so I'm going to use parentheses for that. Bracket is if it's going to be equal to, and then infinity will also be parentheses. All right, for part B, I need to get my x's on the same side. I've got x's on both sides of my inequality. I'm going to subtract 9x from both sides. So I get -7x minus 4 is less than or equal to 17. Now I'm going to add 4 to both sides. And I'm going to divide by -7. Remember, when we divide by the negative, that's where we need to change the direction of the sign. So it's x is greater than or equal to, and then 21 divided by -7 would be a -3. So now I need everything from -3 and up. If I think of that as a number line, I need -3 in every number to the right. So I'm going to have -3 as the lowest value, infinity is the highest value, and now it is equal to, so we're going to use a bracket on the -3. But like I said before, parentheses will be needed for the infinity. All right, part C, 15 minus 6x is greater than or equal to 53. We'll start by subtracting the 15. So I get -6x is now greater than or equal to 38. Divide by -6. Remember, dividing by a negative, we're going to change the direction of the inequality. So I get 38 divided by -6. So I think that ends up being negative 6 1/3. And then for the interval notation on that one, x has to be less than or equal to. So now I want, if I think of this as a number line, all the numbers on the left of this particular value. So we're going to start way down there at negative infinity. And we're going to go up until we get to negative 6 1/3. It is equal to, so I'm going to include the right endpoint, but I will not be including the left endpoint. So we'll have parentheses on that one. All right, there's number 2. All right, on to number 3, absolute value equation. So again, we're going to rewrite the equation. So the absolute value part is isolated. So really we want to get the absolute value by itself. Whatever is in there, we want to get that part by itself first. And then when we get to the absolute value, how do we undo that? We undo that by writing 2 equations. And we're going to solve those then separately. Remember, absolute value, it's going to turn that value is going to be positive. It talks about a distance. It's thinking about the distance from 0. So when we get the absolute value by itself, when we undo it, we are going to write one equation is equal to the positive value, and then one equation will be equal to the negative of that value. And then we're going to solve those separately, and then we should end up with 2 answers for many of these. We could end up with no solution, and we could end up with 1 solution as well. All right, so let's get into it. 3a. I want to get the absolute value by itself, so I want to get that part by itself first. So the first step is going to be subtract 6 from both sides. So now I have absolute value of x minus 1 equals positive 6. And now the question is, how do I undo the absolute value? And we just talked about that. We're going to undo absolute value by writing 2 different equations. So x minus 1 could equal 6, or x minus 1 could equal negative 6. If we think about what's inside this absolute value, that would make 6. Well, if I think about this value in here, it has to either be a 6 or a negative 6. The absolute value of 6 is 6, and the absolute value of negative 6 is 6. So that's why we are going to write these 2 equations and then solve those. So real simple solving from there, add 1 to both sides, and I get x equals 7. Add 1 to both sides in this one, and I get x equals negative 5. And we link those with an OR. So x equals 7 or x equals negative 5. You can plug those back in the original equation. 7 minus 1 is 6. Absolute value of 6 is 6. 6 plus 6 equals 12. Plug in negative 5. Negative 5 minus 1 is negative 6. Absolute value of negative 6 is positive 6. And 6 plus 6 still equals 12. So there is 3a. 3b, again, I need to get that absolute value by itself. There's a 3 on the outside that's being multiplied. So my first step here is going to be to divide by 3. So now I get the absolute value of x plus 7 equals, that ends up, punch that in the calculator, I get a 56. And at this point, I need to undo the absolute value. So we're going to rewrite that as 2 different equations. X plus 7 could equal 56, and x plus 7 could equal negative 56. Subtract 7 from both sides. So I subtract 7 here, minus 7 from 56, and I get a 49. And minus 7 from negative 56, and I get a negative 63. And again, those are linked with an OR. So part C, I've got a couple of different things there that are outside of the absolute value. I've got a negative 2, and I've got a plus 3. So we'll just think about trying to get that part by itself. So I want to get that by itself. So I'm thinking about if that were a variable, I would have to subtract 3 first, and then I would be dividing by negative 2. So those are the steps that we're going to do in order to get the absolute value isolated. So I'm going to subtract 3 first. So I get negative 2 times the absolute value of 5x minus 2. And then when I subtract 3, I get negative 256. And then my next step is going to be dividing by negative 2. So I get the absolute value of 5x minus 2 equals. And I'm thankful here because now I end up with a positive. If this would have been a negative number over here, I know absolute value can never equal a negative. So at that moment, I would actually stop my solving and say there is no solution because I would not be able to get a negative value over here. But it did. It changed to positive 128. So now I know this will actually work out. All right, so at this point, to undo the absolute value, I'm going to be writing two different equations. That's a minus sign in there. So I have 5x minus 2 equals 128. And I'll have 5x minus 2 equals negative 128. And we should all be great at solving these little two-step equations. Add 2, divide by 5, and I get 26. And then for this one, I've got my watermark on there because I haven't been able to get my smartboard hooked up in my house yet. I get negative 126 divided by 5, which is negative 25.2. And there's absolute value equations. We'll be looking at inequalities next. All right, the next step in our solving here is going to be absolute value inequalities. Solve it just like we did with the absolute values previously. Again, make sure that you switch the direction of the inequality sign if we multiply or divide by a negative. And the two things I have starred up there, we need to really make sure that we pay attention to, because when we undo the absolute value and we write our two equations, we actually need to make sure we understand what an absolute value inequality is going to look like, because we have, again, the idea of distance. It's that distance from 0. So if it's a greater than or a less than, we are going to link those differently as we go through those. So we'll go through some examples to look. You guys can read through the examples on the activity sheet and pause and just look at that. But as we go through the solving in 4a, again, I want to get this x minus 5 absolute value by itself. So first step would be divide by 3. So I get now the absolute value of x minus 5 is less than 4. And this is where we're going to split our two equations. So as we split our equations, we get x minus 5 is going to be less than 4. And then what I have to do is when I write my other equation, again, I'm going to switch that to be a negative 4. And I also want to switch the direction of the inequality. When I think about less than 4, I'm thinking about things that are going to be close to 0, right? 3, 2, 1 are less than 4. But I could also have values in here that would end up being negative 3, negative 2, and so on. So I have to have numbers that are also bigger than negative 4. So it really just comes down to this. If you switch, when you switch the sign, the direction of the inequality, then we just switched that from being positive to negative. And then you solve just like we normally would. So here I have x minus 5 is less than 4. I'm going to add 5. And I get x minus 5 is greater than negative 4. So I'm going to add 5 to negative 4 and negative 1. So then here we end up with, think about where that is. X has to be less than 9, everything down here. X has to be bigger than 1, everything up here. So I'm looking at the values, and we're looking with an and. I'm looking at the values between 1 and 9. So to write that in interval notation, I have starting at 1, and I'm going to 9, and I'm not including either endpoint, because in this case it was a less than symbol without any kind of equal to. All right, part B. Two things outside of the absolute value. We've got this plus 3 we need to fix first. So we're going to subtract 3. Then we're going to divide by 6. That was outside over here. And we get the absolute value of x plus 2 is greater than or equal to 2. Again, we're going to split into the two inequalities. So I get rid of the absolute value. So now I have x plus 2 has to be greater than or equal to 2. But I also am going to switch the direction of the inequality, and I switch my positive 2 to negative 2. And then we solve those. So subtract 2 from both sides, and we get x has to be greater than or equal to 0. Subtract 2 from both sides, x has to be less than or equal to negative 4. And we link those with ORs. So this inequality actually ends up being graphed over here, and this inequality is graphed over here. So to write that in interval notation, I've got all the numbers down here on the left-hand side of my number line. So that's from negative infinity up to negative 4. I'm not going to get to negative infinity, but I am going to get to negative 4 because that was an or equal to. And then the second part of it goes from 0, which is included because it's, again, a closed circle, or equal to, up to positive infinity, and the infinity is we are not going to get to. All right, then when we look at part C, I'm going to switch to a new page for that one. So this one, again, I got the two things outside of the absolute value. I'm going to add 7 to both sides, and then I'm going to divide by 4. So then I get my absolute value by itself. Here we end up with a decimal, so we don't need to be afraid of that. Just deal with it. Split up my two parts. Again, get rid of the absolute value, less than 9.5. And then my other rewriting, I'm going to change the direction of the inequality, and I change this to a positive, from a positive 9.5 to a negative 9.5. And then we just solve. So subtract 8. And then in this solving, I have to divide by negative 2. When I divide by negative, we're going to switch the direction of the inequality. So then this side becomes x is greater than or equal to negative 0.75. Subtract 8, divide by negative 2. Make sure that you remember to change the direction of the inequality. So I've got all the numbers bigger than negative 0.75, including it. So I tried to color that one in, and everything less than positive 8.75, again, colored in because we had the equal to. So looking at that in interval notation, I'm going from negative 0.75 up to positive 8.75. In this case, we've got closed circles, so we're going to include both endpoints. And there's number 4. Number 5, here we're going to be solving some polynomial equations. Remember how we do these? Back to our polynomial unit. So set the equation equal to 0. We want it equal to 0 because we're going to end up factoring, and we know if we can factor in something set equal to 0, then we can just set each of the factors equal to 0, which really is what our steps are right here. So first one, quadratic equation here, x squared plus x minus 56. And we're going to just unfoil that. There would be our factoring. Set each factor equal to 0, and then solve those little equations. So there's our first one. Over here on part B, again, not set equal to 0. I don't have a 0 in here, so I want to get 0 either over on this side or 0 on this side. So I decided to move the 3x squared and subtracted that over here, and then I added 14x and added that over there. So now I got to that equation where it's set equal to 0. Now this problem looks a lot like this one. The factoring might be a little different, but the idea is the exact same. I end up with x plus 4 times x plus 8 equals 0. And then again, set each factor equal to 0 and then solve. C and D, a little bit different factoring. Here I have a cubic equation, 4 terms. When there's 4 terms, oftentimes we can look at and try factor by grouping. So when we factor by grouping on this one, that does work. I end up taking out an x squared out of both of those. I end up taking out a negative 1 out of both of these. And I get that common group of x plus 2. So put my 2 common factors together, x squared and then the minus 1. I just keep that x plus 2, really, because if I think about distributing, I'd have x squared times each of those things and negative 1 times each of those things, and that's what it says in that line above. Here now I have a difference of squares, x squared minus 1. We can factor that into x plus 1, x minus 1. And now I have it completely factored down into those linear terms, set each linear factor equal to 0, and then solve. So there would be our solution for part C, those 3 zeros. And then in part D, this one also factor by grouping. You could take out the GCF of 3 if you wanted to. I kind of did it as I went through some of the factoring, but factor by grouping does work in this one as well. Take out a 3x squared out of the first 2, take a 3 out of the second 2. Put those together. I took out the 3 at that point from this part. So now I see this pattern, x squared minus 1. I can factor that into x plus 1, x minus 1. Everything else still comes along with. And set each factor equal to 0, and then solve. So those are going to be the answers for number 5. Now we're going to solve quadratic and polynomial inequalities. We solved that just like we did previously with the equations. Get it set equal to 0, and then we are going to try to factor those. The difference on these then is after we have it factored, factoring finds the zeros when it's equal to 0. Here we're actually looking for when is it greater than 0 or less than 0 or greater than or equal to or less than or equal to 0. So that's a little different. So it says here that we can make a sign diagram as necessary. And then in the examples, we talk about the graphs. So understanding what the graph would look like is also going to be very helpful. That's how I'm going to show you using your knowledge of what the graph would look like depending on the degree and what the leading coefficient is. So we'll get into the questions. So here's the first one. X squared minus 2x minus 35 is greater than or equal to 0. And so we can factor the left-hand side. It's already equal or less, greater than or equal to 0. So if we have that 0 on the one side, we want to factor it. So we can find out when it's actually equal to 0. And that is that when x equals 7 and when x equals negative 5. That really doesn't tell me what the solution is here, though, because I want to know when is that polynomial greater than or equal to 0. So as we consider the graph of that, we realize that it's going to cross the x-axis over here at 7 and over here at negative 5. And then I can use that idea, and then when I know that it's x squared and 1x squared with a leading coefficient that's positive, I know it's going to be a parabola that opens up. So I don't need a real great sketch. I just need to understand the shape. And now I'm looking for when is it greater than 0. So I'm looking for all of this time when the parabola is above the x-axis. So if I just impose a number line over the top, I'm actually looking at this point and everywhere this way, and this point and everywhere that way. And that's where the parabola is above 0. So when the equation is greater than 0 are those two spots. So if we're thinking about that in interval notation, I'm using all of the numbers out here. So that's going to be from negative infinity up until I get to negative 5. We're not going to include the infinity. This is an or equal to, so we will include the negative 5. And then I've got another set of numbers over here that I'm going to include, which would be from 7 to positive infinity. Again, we're going to include the 7, but not include the infinity. So there's 6a. 6b, again, I've got a quadratic. So here I factored out the negative 3. And then I was able to kind of unfoil that trinomial that remained. And again, I found what the two zeros were, x equals negative 4 and x equals positive 2 by doing the factoring. And then thinking about the graph, I see it's going to cross at negative 4, and I see it's going to cross at 2. This time, however, my leading coefficient is negative 3. So if I have a negative leading coefficient and it's even degree, I know it's going to be, in this case, a parabola that's going to open down. So now it's going to look like this. This question is, when is the graph or this parabola greater than or equal to 0? So again, I'm looking for this area. So if I were to think about that as a number line, I want all of this colored in. So if I'm going to do that with interval notation, my furthest number to the left is going to be over here at negative 4. My furthest number to the right then was going to be over here at positive 2. And because it wasn't or equal to, we'll use brackets for both. All right, 6c. This one, cubic graph. I have 4 terms. I'm going to try to factor by grouping, which works out in this case. I can take x squared out of both of those. I can take a 4 out of both of those. When I put these two together, I get an x squared plus 4, and then an x plus 5. I set each factor equal to 0, and then I solve. This one solves pretty easily, down to x equals negative 5. This one, I could factor it further, but because I only have an x that's written once, I can go ahead and just solve that. So set that equal to 0, subtract 4, and now we see I have an x squared equals negative 4. So when that happens, I realize, well, if I take the square root, that's not going to be a real number. So I get x equals positive or negative 2i. So these are not going to be x-intercepts for me. So I really don't have to worry about those for the graph. That's the only x-intercept that I have, is that x equals negative 5. So I can see it's going to cross over here at negative 5. Because this one is 3rd degree, leading coefficient is positive, it's going to start down here and it's going to end up there. Start low, end high. So I don't know for sure what happens in the middle, but I know it only crosses one time at negative 5. It crosses up here at 20. I can see that from this number right here. And then something else happens, and then it takes off and goes that way. So the reason I want to have the whole sketch on there is because I'm looking for when is this greater than 0. So when is it greater than 0? All of this time over here, the graph is above the x-axis. So now I'm going to be at -5. Now I'm not going to include it because I didn't have an equal to, and I want all those values over there. So if I'm going to write that in integral notation, I'm going to go from -5 up to positive infinity. I'm not going to include the -5, so we'll use parentheses because it was just greater than, and we never want to include the infinity. One more for this one. Here, again, we have 4 terms, so I did the factor by grouping. I took out a 2x squared. You could take out a GCF of 2 out of all of these first. I just decided to go ahead and do the factor by grouping. So you see how that shakes out with my factor by grouping. Set each factor equal to 0. I could keep factoring this if I wanted, but I see I only have one x in that factor, so I can go ahead and solve. So add 18, divide by 2, and now take the square root. And now I do have real numbers over here. So I have 2 zeros, one at -3 and one at +3, and another 0 over here at 2. So we'll take a look at that graph as well. Sign diagrams work, but if we understand what our graph can look like, this can also be pretty useful to us as well. So I see it's going to cross at -3, at +2, and at +3. I know that it's 3rd degree, so it's going to be that cubic shape where the endpoints are going to go in opposite directions, and I have a leading coefficient that's +2, so it's going to start low and it's going to end high. I notice I don't have any multiplicity, if you remember that from our polynomials unit, so I don't have any special graph features as it goes through those x-intercepts. So all we're going to do is we're going to go through -3, we're going to then come back down through 2 and go back up through 3. So I didn't hit that one very well, but that's the idea. I've got those crossings at those 3 points. All right, and then the question is, when is it that graph, when is that polynomial less than or equal to 0? So when is it below the x-axis? Well, as I start looking at the graph, everywhere over here, it's below the x-axis. So if I were to, again, draw that little number line, I'm going to do that in a different color on this one. I would be from -3, and that would be a closed circle, and everywhere left. And now I'm above the x-axis, but then over here, again, I get below. So I'm going to be below the x-axis from +2, closed circle, to +3, closed circle. Over here, to the right of 3, I'm back above the x-axis. So to write this one in integral notation, we've got 2 different sets that we're going to talk about. This one over here, which would be from -infinity to -3. We're not going to include the -infinity. We will include the -3 because it's set equal to. Or I can use the piece of the graph that's over here on the right-hand side, which goes from 2 to 3. And we're going to include both endpoints because, again, it could be equal to. So that's using your knowledge of your graph and your factoring to be able to solve polynomial inequalities. Equations that involve roots. Here it says take both sides to the power that will clear all roots. I guess we probably should have started with make sure that what has the radical on it is by itself first. So like in question B, we're going to have to move this -4 first. That's kind of obvious, but maybe not. So we want to make sure we talk about that. But like for this one where we have the square root by itself, we can go ahead right away. Solve as we did previous problems. This one, it's very important that we check our solutions because sometimes when we square both sides or take things to exponents, we need to make sure that the answer we get will check back in the original solution, the original equation, I should say. That's because what happens is there are things called extraneous solution, extra solutions that may arise when we do some of the solving steps that we're going to look at here. All right, so let's get started with solving the first one. So I have the square root by itself over here on the right-hand side. So my first step is going to be to square both sides. So I'm just going to try to draw on these to go a little bit quicker. So I get x squared. The square root and the square are going to simplify out. And we're left with x plus 6. So now I need to solve this. So Again, I've got x squareds and x's, so I have to think about how can I solve those. I can't just start taking square roots because then I end up right back at where I was. So remember, this is a polynomial. I have an x squared and an x, so the best strategy is probably to set it equal to 0 and then try to solve it. So I'm going to move this stuff that's on the right-hand side over to the left-hand side. I get x squared minus x minus 6 equals 0. And then I see this trinomial over here, and I'm used to factoring that. So I'm going to try factoring that down. So x and x would seem to work here. Multiply to negative 6. And then when I do my outside and inside, I should get a minus 1x. So I think a minus 3 there and a plus 2 there is going to work. So there's one of my factors, and there's my other factor. We've been doing that for a long time, so I'm just going to go ahead. X equals 3, x equals negative 2. But we want to make sure we check those. So if I plug in 3 back in the original equation, we'll see if it works. Does 3 equal the square root of 3 plus 6? And 3 equals the square root of 9, so yes, that one does check. There's a good answer. If I plug in negative 2, does negative 2 equal the square root of negative 2 plus 6? Does negative 2 equal the square root of 4? And in this case, the answer is actually no, it does not equal. When we have that square root symbol, the square root symbol means the positive root. So that is the positive square root of 4. So negative 2 does not work as that answer. You can also think about the graphs. If you think about the graphs of the left-hand side and the right-hand side, we look and see when those two things cross. Well, y equals x, the left-hand side would just be that linear equation that goes like that. And the square root of x plus 6 is going to be the square root graph that looks like that. And they're only going to cross one time. It's going to be right there when x equals 3. So this one does not actually work as a solution. All right, let's take a look at the next question. Here I have to do a little housekeeping first. I'm going to add 4 to both sides. So now I have the square root of 2x equals 18. Now I have what has the radical on it by itself. So I can go ahead and undo that square root by squaring both sides. Those are going to simplify out. So I end up with 2x. And 18 squared, punch that in my calculator, and I get 324. Then continue solving, divide by 2, and I get x equals 162. I can quickly check that the square root of 2 times 162 minus 4 does indeed equal 14. 2 times 162 is a positive number. What sometimes happens is these negatives sometimes will creep up and then it's not going to check. This one does. So we're good. There's our answer, 162. Number 7, part C. Here, again, house cleaning. I need to first add 2 to both sides. Then I get the cube root of x equals 5. Now, instead of squaring to undo, I'm going to have to cube because I've got a cube root. So we'll take this to the third power. Third power and third root, those are going to simplify. So I get x equals 5 to the third, which is 125. Check it. Cube root of 125 minus 2 does equal 3 because that means 5 minus 2 equals 3. So there's a good answer. And then on 7 part D, here I already have what's being cubed by itself. So I just have this on the left-hand side, the radical, and then my 3. So to fix that, we are going to cube both sides. Those are going to cancel out. So I end up with 2x minus 5 equals 3 to the third, which is 27. We just go through our other solving then. This is just like with the very first question we had in this activity, real simple linear one. Add 5 and then divide by 2. So I get 2x equals 32 and x equals 16. Take our 16 and plug it in. Cube root of 2 times 16 minus 5. Does that equal 3? And it does. It ends up being that 32 minus 5. ends up being 32 minus 5 is 27. Cube root of 27 is indeed 3. So there's number 7. We'll take a look at number 8 next. We're on rational equations. So we're solving when we have fractions. So what I would like to do is let's get rid of the fractions, and then they become problems just like the ones that we've had on really 1 through 7. So finding the least common multiple of all the denominators, that's the number that all of the denominators would go into, or the expression, because there are going to be variables. Once we clear out all the fractions, then we're going to solve as we previously did. Again, checking those to make sure that they work. And in this case, I think they're all going to work for us. All right, so let's get on to it. The first one, we have numbers in our denominators. So here I just think about what numbers do all of these go into. I've got 4, I've got 3, and really there's a 1 here that I don't have to worry about. So the number would be 12. So what we're going to do is we're going to multiply everything by 12. So that's everything. That's both sides of the equation. So I'm going to multiply by 12 over here and 12 over here. So I'm really going to distribute. So I'm going to have 12 times x minus 4 over 4. I'm going to have 12 times x plus over 3, and that's going to equal 6 times 12. So that ends up being 72. I'm going to write it that way. And here's the idea. 12, I got 12 by looking at 4 and 3. So 12 is really 4 times 3. So I could write 4 times 3 here instead of 12. And I could write 4 times 3 here instead of 12. Because what I want to do is I want to simplify out the fraction. So 4 over 4 is 1. So really, I'm just taking the 3 times this part of the fraction. Make sure I distribute. So I get 3x minus 12. Here, this 3 and this 3 are going to simplify out. So then I get a plus 4x. And then I still have my 6 times 12 of 72 over there. So now I just have to simplify and solve. So I've got 3x and 4x, so together that's 7x minus 12 equals 72. I'm going to add 12 to both sides, and I get 7x equals 72 plus 12 would be 84, and then divide by 7, and I get x equals 12. And I plug it in, and I'm going to get 12 minus 4 over 4 plus 12 over 3, and indeed that does check. So there's my answer. Next one's going to be a little tougher. Now I have variables in the bottom of my fraction. So if I look back at that first one, where did I get 12 from? I got 12 from 4 times 3. 4 and 3 don't have any common factors besides 1. So I just really multiplied those two things together, and there's my least common multiple. Well, now when I have variables, it's a similar idea, but I don't get to use a nice number. But I still think about multiplying these two things together. And we'll see what happens. So I'm going to multiply by 2x times x plus 1. And I'm going to do it times this fraction and times negative 2. Just like we did over here, we did 4 times 3 times this fraction, 4 times 3 times this fraction, and then also times the 6. So I'm going to have times 2x and times x plus 1. And that is going to get multiplied by over here. And don't forget, it also gets multiplied by the fraction over here. And we'll see that some simplifying is definitely going to work here because that's the idea. We're doing it so we get things to simplify out. So what's going to simplify out over here? I'm going to end up with, let's switch to purple, 2x, well, I guess it's going to stay red, and 2x are going to simplify, so I get x plus 1 times 3. I'm going to go ahead and distribute that, so I get 3x plus 3. Here, x plus 1 and x plus 1 are going to cancel, so I end up with negative, don't miss the negative, 4x squared. And over there, I'm going to get, well, negative 2 times 2x times x plus 1. I only multiply two things together at a time, so I'm going to put those two together, and I get negative 4x times x plus 1, and then I'll work on simplifying after that. So we talked about killing kittens back when we were in our rationals unit. This is not that particular case, though, because this is a group, and this is a group. And when I have the same group on the top and the bottom, those are indeed going to cancel out. All right, so I've got some more polynomial solving here to do because I've got x squared and x's. I have to do some more stuff over here. So I better just keep simplifying, and I think I'm going to put it in standard form to maybe help as well. So I get negative 4x squared plus 3x plus 3. Over here, I'm going to have to distribute that. So I get negative 4x squared minus 4x. Now we know when we have a polynomial equation, we want to get it set equal to 0. So I'm going to move everything over to the left-hand side. So I'm going to add 4x squared to both sides, and that's going to be over with this one. And I'm going to add 4x to both sides, and that's going to be with that one. All right, well, that's nice. Negative 4x squared and positive 4x squared, that equals 0. So now I have 7x plus 3 equals 0. Well, I don't need to use any of my other solving for polynomials because this is just a linear equation. So it's 2 steps, and that should be it. So 7x, I'll subtract 3, and then divide by 7, and I get x equals negative 3 sevenths. So there's our answer, and it should work out. Put it in and check, and it does indeed check on this one. All right, 8C. This one, again, I've got numbers on the bottom, so I should be able to do this one pretty efficiently. I've got a 3 and a 5. They don't have any common factors between the two of them, so I'm going to have to multiply by 15. So I'm going to multiply by 15 here, 15 here, and 15 here. So I'm going to do some simplifying. 3 goes into 15 5 times. 5 goes into 15 3 times. That's a group. So we're going to distribute. I don't have a denominator anymore, so it's 5x plus 5 plus I have 3x, and then 3 times 15 I think is 45. Don't have to worry about any kind of x squareds. I do realize I think I forgot a negative over here. So this was a minus 3x. So I want to make sure I get that to be a minus 3x when I look at my check. All right, 5x and negative 3x, those two together can get me to 2x. I'm going to subtract 5 from both sides while I'm here. So I get that equals 40. I divide and I get 20. So I can check it. This one I can actually check in my head. 20 plus 1 is 21. 21 over 3 is 7. 20 divided by 5 is 4. 7 minus 4 does indeed equal 3. So that one does work. All right, last one, 8D. I've got a 5x and an x on the bottom. So like before over here, we put these two things together to make the 15. We just multiplied those. This one I don't have to do the multiplying because they have a common factor of x. So I know x is going to be a part of it, and then I also need to have a 5. So if I multiply by 5x, I realize that that's going to actually simplify out all of my fractions as I keep going. So 5x and 5x, those are going to simplify out completely. So I have x plus 1. The x and the x are going to simplify out. So now I'm not going to miss that negative this time. So minus 5 times 1 is 5. And then over here, I've got 1 times 5, which is 5x. So now we'll work on getting our x's on the same side. I'm going to move it to the left side, or the right side. I don't typically do that, but we'll try it this time. And then 1 and negative 5 makes negative 4. Divide by 4. And x equals negative 1. And when we plug it in, we get negative 1 plus 1, which is 0, over negative 1, which is 0. And then negative 1 over negative 1, which I think would simplify to be a positive 1. So indeed, that does check, and that one also works. So there's activity 3. I hope that helps.